Thanks. Testing.
Okay. And our class like today is by Michael Kirby from Florida State University. And he's going to talk about self-organizing mapping on Grassmannian and Flag manifolds.
Thanks very much. It's a real pleasure to be here. I've had a great time listening to some fantastic talks today. I learned a lot. My talk today is going to be really driven by applications. I'm very interested in solving data-driven problems, real-world problems, where we want to use the mathematics that we can to gain some insight into some, I'd say, relatively challenging questions. Well, one of the questions, for example, would be, can you determine whether someone's going to become contagious within the first 24 hours after they've been infected by a virus? We actually started doing this work about 3 years ago, so we were in time for the new questions that were arising. If you have a bunch of different species and some of them seem to be tolerant to infection, they're like super species. Can you understand what it is about these species that make them special? And can you figure out how to create special species? So these are some of the problems that we're working on. And we're really interested in trying to solve the problems. And so we have to figure out what mathematics are going to come to bear that will be really helpful. So I want to give you a little bit, just a 1 minute feeling about 1 minute description about the ways I think about data. And it's, I think, something that bringing coals to Newcastle in this group, because no one needs to be convinced about the importance of geometry and data sets. So, oops. So how do I go back? There we go. So we have geometric structure in data. We discovered this, like a lot of you, through actually looking at data sets. And one of the data sets that kind of hit us over the head with, if you ignore the data structure, you're not going to get anywhere with the analysis. So if you think about illumination, illumination is one of these really special data sets where if I look at a given person under all possible variations of illumination, what you get is a 10-dimensional convex cone. Right? So now if I want to understand how to do face recognition under variation and illumination, well, I don't want to just take a point in a high-dimensional vector space, right? And we've had a lot of conversations today, a lot of interesting comments about measuring distances between points in high-dimensional spaces. Isn't that helpful? Isn't that useful? Right? So what we're going to advocate is that instead of looking at single points, we want to look at sets of points. And we'll see why that's a good idea. In part, it's a good idea because it immediately gives us this ability to use manifolds. So if I put together a set of data as a point, and I use a subspace approach, I start to ask all kinds of different questions about how I compare sets of data. So we're going to be following this geometric framework. In particular, we're going to look at Grassmannians and flags, and we're going to argue that these are really robust approaches to capture variations in state in data. So if your data is changing, right, you never get to see the perfect data point. You get to see a data point which is a representative for a class of data. And if you want to classify the data, you need to be able to capture this variation. You need to be able to encode in your model how the data varies. And that's what this idea is going to help us do. So we're interested in data reduction, like I think every talk today. And we're going to preserve structure in some form, distances and neighborhoods. Whitney's theorem, Tockins theorem, these are the things I tell people in kind of more broad audience that if you don't know about them, you should think about them, but you guys do. So the questions that we want to address are, how do you compare two sets of data? So I have data set 1 and data set 2. How do I compare them? I think that the EEG problem is an example of that. Are these two sets of data coming from the same brain, for example? How do I compare two sets? Now, often what we'll do, and we'll see we do this here too, is we'll look at things like the Grassmannian. We'll look at a subspace. Well, that's great if you have a tall data matrix, right? What happens if your data matrix is wide? Well, Grassmannian framework doesn't make sense anymore because the distances are all 0. You can say, well, I'll transpose them, but then I'm changing the way I'm comparing the data. Right, so what we're going to do is we're going to show that there's a neat idea where the Grassmannian ceases to be the correct framework. The flag manifold actually is here to the rescue. And we were really excited about some of the results we were able to get. So I'm interested in how you compare two data sets and how do you analyze a set of data sets. All right. Now, behind this, I wanted to revisit as kind of a multiple themes, how to use these ideas in the setting of something called Kohonen self-organizing mapping. Now, this is an old idea, but it's a really pretty idea, and I think it serves as a really good example for how you can do data reduction and create a mapping so that I can visualize data and preserve neighborhoods that are in high dimensional spaces, not distances, but neighborhoods. So that's the theme. So the ingredients for our talk is we're going to look at geodesics and distances on Grassmannians. This is old work, I think probably very familiar to you folks here, by Edelman, Arias, and Smith. And recently with Jiafeng Ma, my graduate student, and Chris Peterson, we've looked at extending this work by Edelman and all on flags. So I'll kind of give a bit of, it's a late, so I'll just go through this quickly because I don't think it's going to be easy to convey it completely. But the idea is that if you have points in a high D space, I can cluster them and I can put centers on them, but then I don't really know how to map these to a low D space immediately. I need to organize, and Kohonen had this really neat idea, which was if you say that centers should be pulled, or vectors or prototypes should be pulled towards data together if they have neighboring indices. So every center has an index. All right. And if the neighbors of indices or the distance between indices is small, then they should be gravitating towards points in this high dimensional space together. All right. So this has the net effect that centers end up organized in the high D space, and neighbors of these centers have indices which are close. They're also neighbors. All right. So that's kind of a really clever trick. And then you have this idea of a topology preserving mapping, which means that if points are high or close neighbors in the high D space, then their indices are neighbors in the low D space. So what's neat about this algorithm is that it only needs two things. So it's an algorithm on a vector space. That's how it was proposed. But all you need to do is to be able to calculate distances between points. And then once you have this distance, you need to be able to move one point in the direction of another. So this is great because this idea that we have with subspaces, with the Grassmannian or the flag, it all will carry over because we just need to do these things, right? Need to be able to calculate in that way. So it's hard for me not to kind of push. You guys really should love subspaces, right? And give you examples of why you should love subspaces. And this is an example of an old piece of work for us, but we love it because what it amounts to is that this very low resolution image of this person, if I just have one, it's not going to be very useful. But if I have a set of these low resolution images, so now I'm back to how do I compare a set of data to another set? So now these are two different people, subject A and subject B. That's a set and a set. Now I'd like to compare these two things. Well, this is really a point on GR 925. So is this another point on the Grassmannian 9-dimensional subspace of R25? And it turns out that you can actually separate the pi database with 25 pixels using the Grassmannian framework, right? Because sets of points are so impressive. And if you stole this data set, or if you lost this data set and someone took it from you, you're not that worried about it because it's low res and no one's really going to complain about their low res image under variation of illumination being stolen. All right, so this is one of the, I'm just trying to convince you that you should think about subspaces. And it turns out that they could be very powerful for solving problems which are otherwise rather hard. This is the framework. You take a set of images, you put them together, you get a point on a Grassmannian, and this is my cartoon, so I can compare these guys. There's a similar, if I have RGB images, these are also points on the Grassmannian. If I have a 1,000,000 pixel camera, they're in GR3 a million. If I have a high resolution, so if I have multispectral imagery, I end up with maybe 100 different frequencies. I'm going to go quickly because we're late, and I'm happy to have people come and ask me questions about it. So the Grassmannian is it's a geometric object. It's a parametrization of the k-dimensional subspaces of Rn. We have all of the different ways to measure distances on this thing. The way we like to do it is we take data and we construct points on the Grassmannian. So I showed you one with the images. This is the same idea with hyperspectral imagery, where I take a collection of points, I get these tall, skinny matrices, I then do an SVD or a QR, and I get a basis, which is an equivalence class for a point. There's an equivalence class for these points. So to measure distances between subspaces, we use principal angles. This is an optimization problem for principal angles. The neat thing about it is they're very easy to calculate. So I'm going to go through that. The geodesic distance is here. We use this quite a bit. We use the chordal distance. You can embed the Grassmannian isometrically in Euclidean space using chordal distance as a result with Conway and Sloan. We've also found this distance here, the pseudometric, just the smallest angle between two subspaces, to be very useful at high dimensions. So this is the Indian Pines data set. I'll just kind of go through it. I want to convince you one more time about the utility of these subspaces. So if I look at one-dimensional subspaces of R200, and I look at two-class problem, this is corn and pasture, pixels in a hyperspectral field, okay? So every point is got 220 bands, and if you measure them and look at them in using angle distances, that's basically what this is. It's in projective space. You're just measuring angles. They're mixed. You get no separation. But if you go to two-dimensional subspaces of R220, you start to get some split. And by the time you're at 10-dimensional subspaces R220, you basically have separated data. Now, this is really great, right? This is what you want from machine learning algorithms. You want your data to be separated. So this is with geodesic distance to show you that the smallest angle doesn't win all the day. Again, you see this kind of splitting of the data. It goes and pull it at 15 dimensions. I'm capturing the variation by getting enough pixels. I get 15 different views, 15 different points in this very high dimensional space. And I take those 15 points together, and I've got a point, an abstract point on a Grassmannian that I can use to compare distances. And suddenly, data that wasn't separable is now separable. So the self-organizing mapping idea is if you take, you have a set of centers. Now they could be points, or they're going to be subspaces. They're going to be either points on a vector space, points on a Grassmannian, or points on a flag. These will all be implemented in the same framework. We're going to use the same ideas. The code will change, but the actual thing that you're doing will be the same. So you're going to present a new point to the system. You identify the closest center, so measure distances between points, and then move the centers proportionally towards that point. So proportionally means based on their index. If the winning center carries its buddies along, let's say, because they have indices which are close to him or her or them. Okay. So this is Kohonen's algorithm. It's an old algorithm. It's a very pretty algorithm. And I want to show you, I think I have time. I'm going to quickly, how much time do I have? 10 more minutes? Okay. I got to show you this one. It's, Okay, so this is, the x's are points. Imagine that you're in 3 dimensions, and maybe it's a Star Trek problem and you need a traveling salesman problem in R3 in the galaxy, okay? So this is, these red points are centers that are going to be pulled towards the data. And let's see what happens. So this is Kohonen's mapping. You see how you get the self-organization. You get the folding initially, and now the folding is gone. It's become a circle. And now what's happening is that as a center, a point is presented to the network, it's being pulled towards the data point. The center is being pulled towards the data point. And they're being pulled towards each other. So if they have neighboring indices, and these are all indices, and you can think of these indices as just integers using modular arithmetic to measure distances so that we get a return trip. And you can see what's happening here. It's rather fascinating, right? That this trajectory in R3 is being pulled towards the data. Now, this may be, so we say, oh, this is in R3, that's how hard can that be? Well, this is a very nice algorithm that carries over very readily to the Grassmannian and Flag setting. Okay. I think since I'm running low on time, I'm just going to show you the 2 other little videos I have. So I want to distinguish between the Grassmannian and the Flag manifold. And what's happening here is that I'm moving the red plane into the blue plane along a geodesic for the Grassmannian. All right. So you'll notice that the axes aren't lining up. And if I want to do the same thing and compare distances on the Flag, you'll see that whoops, I didn't know what I did. This is not my video.
Testing, testing. Testing, testing.
Oh, go back there. We can turn the volume down. All right. It's always a bit of a concern when you go to a movie and try to show something. So I'll just stay here. I'm not going to try to go off. So you can imagine though, right? If I'm making a space go into a space, there's one distance. Now, if I have to take a set of axes into another set of axes, the distance is going to be different. Okay. So I've lost control. I'll just keep chatting. So where am I headed with this? The idea is you take points, a set of points, and I'll have labeled points, I'll have classes, and I'm going to create a bunch of points in this either Grassmannian or Flag. And I want to measure distances. And then ultimately, I want to do a few things. I want to show you how measuring, is it working? How measuring distances you have a lot of benefits when you're working on these subspaces. And then how maybe the takeaway message today is going to be that if you have, let's say, low dimensional spaces, lower dimensional, maybe R5, and I have thousands of points in R5, and I'd like to compare these two sets of data, how do I do it? Well, I'm going to show you a really great way to do it.
It's fully frozen. Yeah.
Okay. So let's talk about the technique. I'm talking about how to compare distances. We know how to calculate distances between points on a Grassmannian, either the chordal distance, geodesic distance. Now, the same thing, let's talk about that on a flag manifold. What is it? Well, first of all, maybe what is a flag manifold? The difference between a Grassmannian and a flag is that a flag has a nested structure. So I'm talking about a full flag would be a one-dimensional space inside a two-dimensional space inside a three up into n dimensions, right? So that would be a full flag. Then there can be partial flags where I might think about I've got a 10-dimensional space and I want to look at a two-dimensional space inside a five-dimensional space inside a 10-dimensional space. And I want to measure the distance between these points on the flag. So the question is, how do you calculate distances? How do you calculate distances on the flag? Well, the equations for doing it amount to having to solve, solve for the geodesic. The big picture is that you have representing the Grassmannian as a quotient space, and you can do the same thing with the flag. So it generalizes very nicely. And without my pictures, I'm not going to be able to make a really great. Maybe. Okay, so I'll try to pick up where I left off. So so we're going to use geodesics because geodesics are things that allow us to move a point towards another point. Geodesics on the Grassmannian are things that were given to us by Arias, Edelman, Arias, and Smith, and our work was to generate geodesics on the flag. So I'm going to dispense with details, obviously, but these are basically I just go and I take the equations from Cahonen and I rewrite them for the Grassmannian, and I get this. And the subspace gets moved towards the centers. And the same way I came up with the circle example earlier, if I put a whole bunch of points on I generate the circle of points on a Grassmannian, just generate them artificially, I can discover them in this index set. So this is allowing me to discover a circle of points on a Grassmannian. I think I'm gonna, this shows us, this is an example of I'm characterizing the points on the different classes, the 10 different classes from the hyperspectral image very well. And I can do it on a biological data set, and it also works well. So I'm kind of shifting gears. I want to accelerate to the flag example, because this is probably one of the most interesting. So a flag is a nested sequence of spaces. And we worry about the dimension. So we think about this being N1, 1, 1, 1, 1, or we can have different subspaces. These are examples of flags. So 1D space in a 2D space in a 3D space. Natural ways flags arise. Somebody just PCA. If you give me PCA on a data set, that's a point on a flag. First dimension inside the first two dimensions, inside the first three, and so on, right? Multi-resolution analysis gives me another example of a flag, nested sequence. So the coarse space inside the less coarse space, and so on. So these are 2 points on a flag because I have 2 data sets, the blue data set and the red data set, and the SVD of each. So the SVD now is a nested sequence, and I can think of the SVD of each of these blue and red points as 2 points. So now I can measure the distance, and the way I measure the distance is I have to move along the geodesic the frame into the other frame. And that's where these pictures arise from. I showed you did not show you the movie, but this is basically the movie idea. So how do we do the calculation for the flag? Well, the structure of the problem is that we need the A's and B's and C's and G's to be, or the G's to be skew symmetric. And then you can calculate the distance between 2 points, arbitrary 2 points on a flag this way, where the lambda I are the singular values of h. Now h has to be found by solving this equation. All right, so I have two square matrices, Q1 and Q2, orthogonal matrices, Q1 and Q2. And I start with H and G random, and I solve this problem, and I solve the problem for H and G. And the way, and at the end, I've got a geodesic path, which is this. It says the geodesic on a flag is that formula. Okay, without more detail. So this is a fun example. If you look at the top row, this is Dobeshay, this is the Haar wavelet of the number 5. This is the actual figure, a Haar wavelet projection on 4 dimensions, 8, 16, and then the full space. It's the Haar wavelet. And in the bottom row, it's the Dobeshay's wavelet, D2. Again, it's exactly what you'd have seen, just using that basis and doing projections on the 4, 8, 16. But what you have in the middle are a lot of fun, because what we did is we took the Haar and the Dobeshays and we calculated the geodesic between these two subspaces. And then we showed how this projection worked by projecting the number onto onto the geodesic. So you're seeing subspaces that are quite interesting, but this is right now it's an example for how this works. You can see that there's all kinds of games one can play now. Grassmannian 5-100 works well, but if I do Grassmannian 2-5, and I do the normal MDS embedding of this type of thing, I go from somewhat separated to not separated. But look at the flag. The flag in GR2395, okay, don't ask me why we picked those. We just picked them for demonstration. You can see that the flag gives us opportunities to separate data. This is an example of this trajectory that we found in a high dimensional space on a flag manifold. And now I guess I'm kind of rushing, but that's all right. What we're seeing here are, if I use 5, 10, and 15 pixels, so the matrix goes from being, the data matrix goes from being 5 by 5 to 5 by 10 to 5 by 15. Now these are the data matrices on the Grassmannian. They're going from square to wide. What we actually see is that for the wide matrix, the Grassmannian is the flag is working really well, right? So it's actually using the data from the SVD to separate these two data sets. Whereas with smaller amounts of data, it's not as good. So this is just a proof of concept that the flag allows me to compare large data sets where the number of data points far exceeds the intrinsic or the ambient dimension of the data. And this shows you that, again, just another example, 1, 1, 3, 5. There's lots of games one can play here. And I can split, with this wide matrix, I can split 3 different classes here. So we're showing that data that in 5 bands is not separable using even the Grassmannian, is separable using the flag. So the idea of using the flag as a pre-processing tool to solve these noisy data problems, I think, is a good one. So I'll just kind of conclude with some observations. Data that's not separable in Euclidean space, and possibly where calculating dimension or distances in Euclidean space is not that interesting, we can do a very nice job separating the data in the geometric framework of the Grassmannian or the flag manifold. This is, of course, promising for us for representing for representations for machine learning problems. The flag geometry provides a useful framework for studying wide data matrices. And although I kind of rushed through it, but the SOM is an effective tool for visualizing points on the Grassmannian, points on the flag, because of the underlying matching of the algorithms, right? That all I have to do is to calculate distances between points and be able to move a point from one in the direction of another point. Thank you.
Hi, I think I didn't understand how the geodesic on the flag is different from the geodesic on the Grassmannian. Could you explain that?
Yeah, well, the picture was supposed to show you, right? So the geodesic on the Grassmannian means I just move one subspace into the other subspace in the shortest way possible.
Mhm.
Now, geodesic on the flag means I have to take and respect the nesting of the two spaces. So that this one space, the 1D space has to go to the 1D space, the 2D space has to go into the 2D space, and the 3D space has to go into the 3D.
So does this mean that like you can only compare, that like there seems like there's kind of like some compatibility thing that with the flag, right? That there needs to be like the same number of like you have to do one dimensional compared to one and then 2 to 2 or something.
Yeah, well, that's right, they do. But the thing is, we're going to start off with points that are both, the data now are going to be, let's say, for example, these Y data matrices, and we're going to put them into, let's say they're in Rn, and so the representation for the data will be n by n matrices. So that we'll have bases effectively for each data set. Then the basis and the way the axes of those bases are oriented is based on the data. That's why it changes if I have more points, because the actual axes of the bases change. So the compatibility it's not really a problem in the sense that if I take the assumption I'm going to have more data points than my dimension, then I'm always going to be mapping one space into the other space.
Further question or comments or from virtual participants? If not, let's thank Michael again.
Thank you.
Thanks for all of you and have a great supper and see you tomorrow morning.